Okay, I've got 12 o'clock. I have Kana, Arushi, Jack, and Jordan. I do not see Garrison, Terrence, and I do not see Misael. Okay, so as we start our lecture today, let's make sure that we have an opportunity to answer any questions or any outstanding questions that you might have right now. So let's pause for a moment. Any outstanding questions on anything that we were discussing the last time we were together yesterday, or any material at all? I forwarded all of you information back. What I realized actually yesterday when I was going through my book is the last quiz that we had, quiz number 7, I graded it, but then I never saw you again. So I have quiz 7 for you. I will make a copy of those and forward those copies of the quiz to you later today. So you'll receive that. And then I shouldn't have any other property that's yours. You should have copies of everything that I've gone through and looked at. Questions about anything that we've talked about so far? Sinusoidal steady state circuits, how cool they were, how awesome they are. I'm going to take one more extension in the world of sinusoids. It's going to be real. I hope you really enjoy it. You might not enjoy the mathematics, but at the end of the mathematics, I hope you enjoy the results with regard to transformers. And in particular, we're going to talk about ideal transformers so that you can start to understand some of the cool things that we do with transformers, why they're used, how they're used, and what it is that they can do that's particularly important to us. Any questions?
When are the homework problems due?
Homework would be due this Friday. So Friday of this week, and I know what your question is, Jack. That'll be next Monday then. Next Monday, because we don't have class on Friday. So next Monday. Excellent question. Thank you. Other comments or questions? Okay, not hearing any. We're going to expand into the world of transformers, and that means a flashback, if you will, a flashback of mutual inductance. So I'm not going to go into great detail about mutual inductance, but I'm going to try to do this picture that we did the last time again, and I'm going to find out how tough it'll be to do here. So we'll have a coil over here on this side. We're going to have a coil over here on this side, and we know that an inductor is nothing more than a wire wrapped in a coil, a wire that's wrapped in a number of turns. So over here, let's call this coil number 1. And let's call this one over here on this side coil number 2. So number 1 is on the left, coil number 2 is on the right. And this is not pretty artistry here, so forgive me for the artistry. So let's assume that we apply a voltage V1, and that voltage can be applied by a source, obviously. So whatever it is, maybe it's a voltage source. And then over here, a voltage V2. Okay? So when we have these coils and we couple them, basically what we have is the following. So current I1 flows in this direction through the coil, and I'm going to draw over here. I'm just drawing these directions. They could be opposite. A current I2. So that current flows through this wire going in this direction here. And as wires pass current, we know from physics, by Faraday's law, we know that a magnetic flux or a magnetic field is created by the wire. And we talked about this last time, that it operates in the right-hand rule. If you point your thumb in the direction of the wire where the current is going and wrap your fingers around in a curled manner, the flux point in the direction of your curled fingers. So what's going to happen is we're going to get flux. So I'm going to show you over here, like this current I1 would have a flux that would wrap around it like in this direction here. So using the right-hand rule, it would actually point in this direction like that. Of course, you can't tell because I'm doing this on a two-dimensional plane. You really can't tell whether or not I've drawn that in the right direction or the wrong direction. So let's not lose any sleep over that. But here's the bottom line. When we have this inductance that comes from this coil, a couple of things happen. So we end up with some inductance that comes from the coil, from the current that's flowing through it, and then we have some inductance that comes from the coil of the other current that's flowing through that opposite coil. And so let's just look at this way. So let's assume, if you will, that I have some flux that goes in this direction. Okay, and if you're seeing things the same way I'm seeing them, you'll see that the flux goes like that. And let's call this flux PL1. So it's the flux from inductor number 1. At the same time, this flux, we know, I can draw oodles and oodles and oodles of circles of this flux. This flux goes out there and further, but I don't want to look at those. I want to focus just on a tight picture. And so I want to focus also on some flux that does the following. So kind of like this, if you will, and then it cuts through over here and then back. So there are multiple surfaces in which we can see this, okay? And just for the heck of it, I'll draw this direction as phi 2,1. So it's the flux, and it's the flux that is cutting through coil number 2, but it comes from coil number 1. So you notice number 1, the last number, is the number where the flux is coming from. It's coming from coil number 1, but it cuts through coil number 2. At the same time, we would end up with this over here. And if I had colors, you'd love me for using my colors, but there's a flux over here. It comes from coil number 2. And at the same time, there's a flux, and I'll just draw it as an inner loop that cuts over here through this coil. Okay? And I'll call that flux V12. And you don't have to worry about getting these correct because we're not going to talk. I'm just doing this for illustrative purposes only so you can see what's going on. So let's call this V21. That is flux that cuts through coil 2, but is created by current I1. Here's the terminology your author used: threads through. Threads through coil number 2, but is generated by coil number 1. So what's important is when flux ends up threading through a coil, and if we close that loop, we get an induced voltage, which will generate a current. That's what happens. And so that's why it's important to understand this concept. So the other one is obviously flux that threads through coil number 1, but it's generated by coil number 2. Okay? So I have these two terms. So what I want you to think of is coil number 1 over here. When we look at this coil number 1, it generates both flux L1 and it generates flux V21. Okay? So coil number 1 generates both L1 and V21. So it generates both of them. And so the total flux that's generated, and if you look at this in your book, your author talks about this, but we're not going to lose any sleep over it. the total flux that is generated is phi L1 plus phi 2-1. It's additive. No big deal. Don't worry about it. So it generates both of those. So phi 2-1 is called the self-inductance. I'm sorry, the mutual inductance. Look at what I'm doing here. Phi 2-1 is called the mutual inductance. So there's a voltage generated in coil 2 that comes from coil number 1. And we saw that already with mutual inductance. So that's the mutual inductance. That was the M term that we used. So this phi 2-1 that we have here, right here, this outer circle, is cutting through over here. When it cuts through all of these loops, every one of those loops causes a voltage to be generated. And so the more loops that we have, the more interesting this is. So on this side, we say we have N1 turns over here, and over here on this side, we have N2 turns. So the number of turns determines what that mutual voltage is going to be. Okay, so the turns are important. So phi 2-1 is the mutual inductance term. Obviously, phi L1 is called the self-inductance term. So here's what's interesting. What's interesting is the following. When I look here at this circle here, okay, at phi L1, and when I look over here at phi L2, at this loop, to us in the world of transformers, that is not a good thing, because a transformer, the purpose of a transformer is to cause all the flux from here to find its way over into this coil. That's the purpose of the transformer. So oftentimes when we look at phi L1 and phi L2, we use a terminology for that. So phi L1 and phi L2 in the world of transformers are called leakage flux. So we're losing that flux. Okay, it does not cut through the other coil, so it's leaking out on us. It's kind of like you sprung a teeny bit of a leak in a garden hose, and that water doesn't make it to the end of the hose. This is flux, it doesn't make it to the other side. And so what we do in a transformer, as we know, because we talked about this, so we know that transformers are designed to get as much flux from one coil in passing through or threading through the other coil. To get as much flux from one coil to thread through the other coil. I dot E dot reduce the leakage That's what a transformer aims to do, to reduce the leakage flux. We want all that flux going from one coil and passing through the other coil. That's ideally what we're trying to do. Okay? Pretty good? Now, the question is, how do we do that? So the answer is we have to find something that will cause the flux to want to move in that direction. And the answer is, think of this just like a resistor. We find the minimum resistance that we can, that all of the fluxes going to want to go through that minimum resistance versus going through a much higher resistance. And if you take a course in transformers and electromagnetic theory, you'll see that they use a terminology that treats it just like it's a resistor. But it's not a resistor. And so we talked about what we do. Anybody remember what we do in these transformers? We use a ferromagnetic core. We use a magnetic material that looks like real low resistance to a magnetic field that causes the flux to want to pass through the magnetic material. And then we just take that material and we pass the material inside the coils of both sides, coil number 1 and coil number 2. So we use a ferromagnetic material and pass it through both coils. So think of that coil as being very low resistance for the flux. So all the flux wants to jump on the coil and it passes through the other side. And we showed you what that looked like, sort of with a what I call a toroidal core. But it doesn't have to be toroidal. It can be anything. So there are textbook pictures that kind of look like this if you look at them. And we've got this face up here and this over here and like this. And so what we do is, so this is ferromagnetic. And we just wrap a coil around it like the following. Right from behind. And we do the same thing on this side over here. Like that. And so now this thing sits right in the middle. All that flux we know from the right-hand rule, we know that flux is passing around the inside as well as the outside, but it causes all that flux to want to pass through the inside of this coil. And then now the flux moves through this coil or core like in the following manner. Okay? And when you do that, it's almost like you can't really tell which coil it comes from. So it just wants to do that through that core. That's how we do it. All right, that's all I'm going to say about transformers and their makeup. Now I'm going to focus on the beautiful equations and how we transition from two coils that just start as mutual inductance coils, and we're going to make them we're going to transition them into becoming transformers by finding out what must be true about transformers. So here we go. I want to consider the following circuit. And I'm going to go right to the frequency domain here. So this will be my current I1 phasor, plus minus V source. And here, a lot of textbooks will leave this out. I'm going to put it in right now, and then we'll worry about what to do with it later. Z sub S, we'll talk about what all of that is. Continue forward with me. So we're going to get to A and to B. Now here comes the makeup of the transformer, and I'll show you that. So every inductor has internal resistance. Every resistor has internal inductance. So here, let's call this J omega L1. Let's call this over here R1. Okay? On the other side, the mutual inductance is going to couple these two coils. I'll put that there. I'll put its internal resistance, R2, J omega L2. And then outside of that over here, I'm going to put a load, Z sub L. Okay, so everything's identified in the circuit. We'll talk about what all of these things are. So I wish I had colored markers with you. I'm going to put a little dot here, a little dot here. Let's just, for the heck of it, let's call this C and call this D. Not sure that we really need those, but go ahead and do that. And let's call this current right here I2. So I have I1 and I have I2. And let's call this voltage right here V2. V2 is the voltage across Z sub L, but at the same time, it's something else as well. All right, let's start here. So everything inside this box is the transformer. So it's going to be a transformer that needs to be mutual inductance. So here's the mutual inductance. And so I'm going to put dot notation. So I'm going to put a dot here. I'm going to put a dot there. Dot notation is still important for us. There are a lot of things in inductors that we're going to be able to blow off and ignore, which is really cool. Hopefully it knocks your socks off. But one of them that we can't ignore is the dot notation. We still need to know the dot notation. Now remember what we did before in the dot notation. We put an M on it. But remember in the equations, when we were writing the equation, we had, for example, M di2 dt. Do you remember that? I'm going to erase this in a moment. So when we were looking at our equations, when we're looking at what the mutual inductance term is, we still get this derivative. So since we have a derivative, we know what derivatives do to us with inductors in the frequency domain. They give us the j omegas that we have with the L's, just like we have L di dt. So this impedance here is j omega M. That's the mutual inductance term for its impedance. J omega M, J omega L, J omega M. Okay, all of this over here, from here to here, this is all the source. So therefore, V sub S is the source voltage. And Z sub S is the source impedance. We've never thought about this before. One of my favorite experiments is actually to find out what the impedance of your source is, and there are ways to do that. Sources have impedances. If you have a battery has an impedance. So sources have impedances. And so we're going to ensure that we put a source impedance in here to show that the source has an impedance. Oftentimes what we've done in this course is we have ignored our source impedance. We've always set it 0. Over here in this direction, this is the load that we want to put on the transformer. So this is the load. For the transformer, R1 and R2, it's the resistance of the coils. I'll say in the coils. And obviously L1 and L2 are the inductance values, the inductor values in henries. So that's obvious, but we'll state it. So that is our standard circuit. That's what it looks like. And we're going to make some modifications to this box. So right now, I want you to know right now what we're dealing with is what we call a linear transformer. And we're going to work our way from this linear transformer to the ideal transformer case. And we'll figure out what the difference is between a linear transformer and an ideal transformer. So here's what I'm going to do. I'm going to do some analysis of this transformer. And what I'm going to do is I'm going to write a KVL around what's called a primary loop. So what we do is we call the first side with the ones in them. So everything on this side over here, we call this the primary, and this is the secondary. Primary is side number 1, secondary side number 2. Nothing that you wouldn't expect. So let's write a KVL equation. Around the primary loop. So, KVL equation around the primary loop. What does that do for us? Let's slide back. There's our primary loop. There's the current I1. It goes around this loop just like that. That's pretty cool. So here we go. Minus V sub S plus I1 times Z sub S plus I1 times R1 plus I1 times J omega L1. All right, now let's see who's going to be really good. So I'm going to get from this, I'm going to get an I2 J omega M. So let's write it. J omega M I2. I'm going to sum those up. They're going to be equal to 0. And I want you to tell me what goes here. I'll erase that in a moment. Is it a plus sign or a minus sign? Do you remember how to calculate that? So I1 goes into the dotted sign, the dotted side. I1 goes into the dotted side. Here it is. I1 is right there, goes into the dotted side. But I2 enters the undotted side. So what do we choose, the positive or the negative sign? You have to sneak back and look at your notes. Positive. Go ahead, I missed that. Somebody chimed in?
Negative.
That's correct. It's a negative. When they enter the opposite sides, the one's in the dotted, the other's in the undotted, we get the negative sign. So we sum those up, they're equal to 0. Obviously, we can group all of this together pretty easily. So here we go, let's group. So we have parentheses, Z sub S plus R1 plus J omega L1. All of that multiplies I1 phasor plus minus J omega M I2 equals V sub S. There's one equation. One equation. That wasn't too bad. That was nice. Let's get equation for the second loop. Again, that's a pretty easy loop. Not a lot going on over here. Let's go in the direction of I2. So we're going to go around the secondary loop. So when we do that, you can see that we have, it's going to be I2 times J omega L2. I2 times J omega L2. Okay, but don't forget the mutual inductance term. So we get a term from J omega L1. And I'm sure you can see that this is all, I'm sorry, not J omega L1, J omega M. I'm sure you can see that that is a negative. So we're going to get that. And then we have plus R2 times I2 just like we're doing a mesh equation, plus ZL I2. Sum those up, they're equal to 0. Clean them up. We have minus J omega M I1 plus, and now we'll group all these together, R2 plus J omega L2 plus Z sub L, L for the load, all that times I2 is equal to 0. So here we have equation, here we have an equation. So we'll take a look at those two, but we're going to try to simplify this a bit. Okay, I just want to go back to the circuit for a moment, help you understand something that's really cool about transformers. So we don't know a lot about transformers. I will tell you, most of you know communications was my specialization in electrical engineering, and transformers are used in the communication field in a lot of places. But really what they're used for, believe it or not, it's going to be something that sounds really bizarre. They're used to match impedances. Match impedances, what do you mean by that? Well, we talked about how we can dissipate a maximum amount of power in a load, and we looked at that in the case when we had a Theveninized circuit. We can maximize by setting the load resistor equal to the Thevenin resistor. Well, one of the things that we often do is we have to make those impedances match in a particular way. And we can use transformers to do that when the impedance is in the complex world. And it can change with regard to frequencies. So they're used for that. But the other thing I really want you to notice, it's really cool. Notice that this is completely isolated from this. Completely isolated. What I mean by isolated, I2 doesn't leak out of this second loop, and some of it leak into where I1 is. They're completely separate terms. And this is kind of like when we had the op amps and we were looking at a unity gain op amp and how op amps can provide isolation from the output to the input. Transformers can do that. So they can match impedances, they can isolate portions of a circuit. The other thing that they can do is they can eliminate DC from your circuit. Why? What does DC look like for an inductor? Or what does an inductor look like to DC? An inductor looks like a short circuit. So that voltage on one side that you get from the DC is 0 voltage. And so that doesn't affect anything because 0 voltage gives you 0 current from the DC term. So you've got no flux linking the other side and it doesn't pass to the other side. So you can pull DC out of your circuits when you don't want it to be there. So if you have DC going through your speakers and your sound system, it can do damage to your speakers because it causes problems with the noise and the rattling of the speaker. So you can eliminate that by putting a transformer on it and make sure you don't get the DC through. Okay, now let's do the following. Let's take these two equations and let's establish some definitions. So let's define Z11, and Z11 is going to be the impedance of the primary loop. So Z11 is defined to be the total impedance seen in the primary loop. And so we know the total impedance of the primary loop is nothing more than the sum of those three right there, if you look at that primary loop. So Z11 is equal to Z sub S plus R1 plus J omega L1. And this is just going to prevent us from writing a whole bunch of terms as we're going through our work. We'll just Z11, we know what it is, we'll come back and we'll get it when we need to. So we're going to put a box around that because we'll need to get that later on. Not right now, we'll need it later on. So just remember equation number 1. That's equation number 1. At the same time, we're going to get the impedance in the secondary loop. So we'll call that Z22 is defined. We'll put a definition on top of that. is the impedance in the secondary loop. And what does that look like? Well, we'll call that equation 2. C22 is defined to be equal to R2 plus J omega L2 plus Z sub L. So we're going to do a little bit of math today. Today's going to be a math day. Not a math concept, a math day. And so we're going to try to simplify things that we're carrying around. So if we look at that, then we can go back to our equations from up above, and we take these equations that we have here, and we can rewrite them the following way. See if you agree with this. So Z11 times I1 minus J omega M times I2 is equal to V sub S. The second equation is minus J omega M I1 plus Z22 I2 is equal to 0. So those are our two equations. And if we needed to, we could solve for both I1 and I2. So we can solve very easily. And the way I would solve this is I would use Kramer's rule. I'll spare you the math. And this is what we would get if we needed them. I1 is equal to Z22 divided by Z11, Z22 plus omega squared M squared. Interesting. All times V sub S. And then I2 is equal to J omega M Z11, Z22 plus omega squared M squared times V sub S. So you can see they both have the same denominator. They both multiply V sub S. Now, what's really important here is the ratio of I1 to I2. So looking at this equation right here, we can solve for I2. That's pretty easy. And so C22 I2 is equal to minus J omega M times I1. Now I could solve for I2, but really what I want is I want the ratio of I2 to I1. So see what happens when I get I2 over I1 or I1 over I2. Because I can look at either of them if I want to. So if I look for I2 divided by I1, so I divide both sides by I1, get a phasor on that. There's my I2 over I1, and this is what I have. I have to divide both sides by Z22. Now I have the result that I'm after. It's minus J omega M. Where's the minus? How did I get a minus in here? This is a plus. I brought it to the other side of the equation. That's a plus. It's positive J omega M. Okay, positive J omega M divided by Z22. Now I want to store that as equation number 3. I want to note the following. I'm going to note it here, and then I'm going to insert something at the end. Okay, note. If one of the current directions was taken different, So let's see what would happen. Just remember, back up in the original equations, if one of them was changed, that negative there and that negative there would change to a positive, which would indeed give me a negative right there, right here. So we would end up with a negative in this relationship. I just want you to remember this. Just remember it. So it can be either positive or it can be negative. I2 over I1 is either negative j omega m over z22, or it's positive j omega m over z22, depending upon the original circuit and whether or not I have I1. So now I have I1 is coming in this direction and I2 is going in that direction. In this direction, it's going into the transformer, or here it's coming out of the transformer. So I could have them both pointing in, I could have them both pointing out, I could have one in and one out. If one is in and one is out, over here, if one is in and one is out, it's a positive sign, that's what I have. If both are in or both are out, then I get a negative sign here. So I want to generalize this to be able to handle every single possible transformer. Every possible transformer. I want you to also observe the following. Transformers are real cool devices. They are 4-terminal devices. Remember, the transformer is inside the dotted line. The transformer is inside of that. And that transformer, if you block off, in your mind, block off everything that's outside of that, that transformer can be used in any direction. In other words, I could make this the primary side and put the source over here, and I could put the impedance over here, or I could do it the way I did it. It doesn't matter. Transformers, you can flip them around. Transformers are devices that have 4 leads, and you can put them in forwards or backwards. And you'll see later on how that affects what happens with the transformer. Okay, so far so good? Everybody good so far? So we've established 3 important equations. Before we break, I want to get in another important equation, and that important equation is I want an important equation that relates the ratio of the voltages. Why do I want the ratios? Because in a transformer, in an ideal transformer, it is the ratios of the voltages that we look at. It's something really important happens there. So now I want to find a relationship for the ratios of the voltages. Please recall, in this circuit, again, here's the transformer. So the voltage that we're after is this voltage right here. The voltage at the input of the transformer. V2 is the voltage over here at the output of the transformer. Notice 2 things. V1 is not only the voltage at AB, it is also the voltage from the source and the source impedance. So you can look at it as it's the voltage over here from this point to this point, or it's the voltage over here from this point to this point. It's the same thing. Same thing can be said for V2. V2 is the voltage across the load from this point to this point, but it's also the voltage across the transformer, this point to this point. So it's both on the left-hand side or on the right-hand side of the dotted lines that I've drawn. So what I want is I want I1 and I2 are the currents in and or out of the transformer. That's good. Now what I want is I want the voltage at the transformer. So this VS is no good to me. I need V1 and V2. So how do I get the voltage V1? So I need the voltage V1. So what is V1 equal to? Well, it's I1 R1 plus I1 j omega L1 minus j omega M I2. That's what that is. I can group that together. V1 equals R1 plus J omega L1. By the way, that is the impedance of the transformer on the primary side. Okay, the impedance of the transformer on the primary side, all that times I1 minus J omega M I2. That one wasn't too bad. Now the question is, what is V2? V2. Well, we can write V2 in terms of I2. And we can write it in terms of the impedance of the transformer, or take an easier choice, which I'm going to do for a particular reason. I want V2, look at V2 as the voltage across the load that we end up hooking up to this transformer. So let's take that easy approach. So V2 is simply equal to Z sub L times I2. Okay, again, we could have looked at this in terms of J omega L2 and R2. We could have done that, but I am opting for this one. I know where I'm going. I know what result I'm after, and I want the impedance of the source to be out of the equation, and I want the impedance of the load to be out of the equation. I want this and I want the impedance of the load to be in the equation because we're going to control the load. Okay, so what we have is V2 is equal to Z sub L times I2, right? But if I substitute for I2 in these two equations, we have I2 where? I2 is, I want to use this relationship right here. This one that I wrote there. So let's recall from this, I2 is equal to the, I'm looking at the box now, from the box. I just put an I1 over here, and that's what I2 is equal to. So I'm going to use that, okay? Come down here, just remember that I2 is equal to J omega M over Z22 times I1. All right. Great. So let's do that substitution. So when we do that substitution, we now have V2 equals C sub L I2, which equals Z sub L times J omega M divided by Z22 all times I1. Okay, and just as a reminder, we know that V1 is equal to, so here's V1, so V1 rewrite that. So I have R1 plus J omega L times I1 equals R1 plus J omega L L1 times I1. And then I have minus J omega M divided by Z22. Let's get this right first. So this is the J omega M. Now, J omega M over Z22. I'm getting really sloppy today. times I2, right? I2, I'm putting in for all of this I1, correct? So for this I2, I'm substituting that in. That's what's going down there. So now you see that everything's in terms of I1. So now I have V1 is equal to R1 plus J omega L1. Now, minus J times J, positive 1, omega times omega, omega squared, M times M times M squared, all over Z22. And all of that, all three of those terms multiply I1. Why did I want to do that? I want this ratio of V1 and V2. So here's V2, here's V1. Let's take these two. Let's take the ratio. So V2 over V1 equals, I'm just rewriting the equations. So in the numerator, Z sub L, let's get it, don't throw it away. Z sub L, J omega M over Z22 times I1 divided by R1 plus J omega L1 plus omega squared M squared over Z22 all times I1. Cancel, cancel. So here we have the result that we're after. So this will be our equation 4. Therefore, V2 over V1 is nothing more than ZL times J omega M divided by Z2. So let's write that first. CL times J omega M divided by Z22 all over R1 plus J omega L1 plus omega squared M squared over Z22. You and I know we hate when we have numerators and or denominators that have fractions. So I'm going to multiply top and bottom by Z22 to get the final result that I'm after. So here it is. V2 over V1 equals Z sub L times J omega M. So I'm going to put the J omega M here. Divided by R1 Z22 plus J omega L1 times Z22 plus omega squared M squared. And these equations are going to prove to be very fruitful for us when we look at transition from the linear transformer to the ideal transformer. So that will be equation number 4. So equation number 3, really important. Where is it? My ratio, I didn't put a 3 on it. Here we go. This is equation number 3. So we have 1, 2, 3, and 4 is equation number 4. Those are the equations that we're going to refer back to when we start substituting in certain things. So when we want to substitute in what is Z22, you need to know what it is. That's in equation number 2. What is Z11? That's in equation 1. What is the ratio of the voltages? That's equation 4. What's the ratio of the currents? That's equation 3. Okay, let's pause and take a break on that. We'll come back in 5 minutes and we're going to pick it up and see where we're going with these ratios and how they can be helpful to us in terms of the ideal transformer. So I'm going to put this on pause and then we'll come back in about 5 minutes. Okay, how are we handling this so far? I know it's a lot of math today. What do you think?
Good so far.
Good so far? I don't want you to focus too much on the mathematics. I want us to focus on the results. And I know you don't know where I'm heading right now. Every once in a while, what we have to do as instructors is we have to decide how technical do we want this to be, how much rigor do we want to include, and how much do we just do hand waving and skip over a whole bunch of things and say, and this is the result. And this is one of those times. So what I decide as an instructor is I decide that I want to make sure that you've got some knowledge of the mathematics behind at least a handful of different topics. This is one of those topics that I'm choosing to make sure that you understand the mathematics behind it. And so for that reason, I'm spending some time on it. Right now, it's really ugly. The math is ugly. Not even sure what we're going to use it for, but it's coming up. It's coming up very quickly. So we're going to continue to work our way through this and see exactly what this is leading to. All right. So I want one more piece for this linear transformer. So all of these are equations for a linear transformer. You put in mutually coupled coils in a circuit like the one that we just designed for you, and that would be a linear transformer, and all these equations that we've developed would be true. There's one more, and it has to do with impedance. So we're going to see exactly what that is. So here's what we want to know. We want to know the following. What is the impedance seen by the source? What's the impedance seen by the source? And so I want to remind you, scroll back, scroll back, scroll back, scroll back. Look at all this beautiful work we did. The impedance is right here. Impedance seen by the source is looking in here and here. What would be a great notation to use to call this impedance something, looking in here? What do we call that impedance? We've used this notation before.
Z equivalent.
Okay, and then Z equivalent is equal to what? Give me something, another form. You are exactly right, Jack. Z equivalent equals, we've used another form as well. I've helped you. Z. What subscripts do we use?
Is it Z theta?
Nope, not Z thev. Z seen at the terminals AB, we just called ZAB. We've used that a handful of times this semester. ZAB. Okay, so what I want you to observe is ZAB does not include the internal resistance of the source. That's from the source. So it's everything else. So I hook up this source, that's what I hook up to the rest of this, and I want to know what is the impedance that is seen. And we're going to see something really interesting with this. I hope you find it interesting. So, ZAB is what we are after. So, can you see that if I look back at the following, V sub S, and I divide V sub S by I1. First of all, do you agree that V sub S divided by I1, do you agree that that's an impedance? So back to our picture. VS is here, I1 is here. So there's VS, there's I1. That's right at those terminals right there. So that'll give me the equivalent impedance looking in here. Do you agree with that? That's the impedance looking in here. So if that's the impedance looking in there, then VS divided by I1 should be equal to Z sub S plus ZAB. Aha. So that means CAB must be equal to V sub S over I1 minus Z sub S. Just bringing the Z sub S over to the left-hand side of the equation. Okay, well, let's work with that. ZAB equals VS over I1. I gave you I1 before. I'm not going to rewrite it here for you. I'm just going to put it into the equation, divided by I1. I1 was Z22 divided by Z11, Z22, plus omega squared M squared, all times Vs. So it's that minus Z sub S. Okay. Cancel, cancel causes what? This denominator to flip, right? More math, Z11, Z22, plus omega squared M squared divided by Z22. Wow. Minus Z sub S. Okay, that's not too bad. That's equal to Z11 plus omega squared M squared over Z22 minus Z sub S. Now what I'm going to do is I'm going to substitute in for Z11 and I'm going to substitute in for Z22. So this is equal to Z11 was all the impedance that we had in the loop on the right-hand side. So that was R1 plus J omega L1 plus Z sub S. That's that term. Plus omega squared M squared divided by Z22 divided by R2 plus J omega L2 plus Z sub L. Okay, and then minus Z sub S. Oh, wow, look at that. Gone. Of course, we knew it was going to disappear. It had to. Because it's not part of the terminals AB that we're looking into. So here's the result that we're after. ZAB equals Z11, I'm sorry, R1, I get my replacement in here, R1 plus J omega L1 plus omega squared over R2 plus J omega L2 plus ZL. And I know right now all of these equations are ugly because they're all just in terms of all of these unknowns. They're really not unknown. We'll know what they are. I'll give you the values. You just plug them into this equation. All right, watch this. That's the impedance of the primary coil. Whoop, undo that. Where did that disappear from? Here somewhere. Z11, Z22. It's so weird how that happens like that. All right, scroll, 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 get to the circuit, go back to this circuit. So we start to erase some things. So this was R1 here. So R1 plus J omega L1, this is the primary coil. Here's the secondary coil. So we're looking in here, right, in this area here, excuse me, what we're seeing is the impedance when I look in is that's there, but there's another term. And that other term is this last term right here. And this term is called the reflected impedance. Notice it has everything to do, did I lose my M squared? Notice it has everything to do with the secondary, R2, L2, Z sub L. So this is called the reflected impedance. It reflects back to the primary side. So that mutual inductance causes an impedance on the secondary to look like there's something on the primary. But notice it's not just Z sub L. It's more than that. It's omega squared, M squared, divided by R2 plus J omega L2 plus Z sub L. So it causes it to look like the following thing is taking place. This is what it looks like. V sub S. Z sub S. Here's my coil. R2. J omega L2. And I'm just going to call this Z sub R right now. I'm not going to use that notation later on for this reflected impedance. That's what that circuit looks like. And now there's nothing over here. Isn't that bizarre? It looks like one simple circuit. So that reflected impedance is going to roll for us. It gets reflected from the secondary to the primary. Okay. Now let's start simplifying those equations even more. So the ideal transformer. So there are a couple of things. Before we get into the equations for the ideal transformer, I skipped a handful of things with regard to mutual inductance and the whole inductance thing and how it works. So I wanted to find a measure of how much leakage flux we have. A measure of how much leakage flux, or the ratio of leakage flux. And we call this the coefficient of coupling. How well coupled are these, okay? The coefficient of coupling. And here's what the coefficient of coupling is. First of all, we call it K, and it is defined to be equal to M divided by the square root of L1, L2. Now, we did not tell you anything. We're not going to use a lot of K. I just want you to understand this. We're not going to use it in any equations that we do. We just got to understand. So you don't know where that K came from because I skipped that step for you, but I want you to understand the following. I'm leaving out the details, but we know that K can never be greater than 1. M can never be greater than the square root of L1, L2. So the details are left out. But the range of K is the following. That's its range. Okay? From 0 to 1, which means the following. M is restricted and cannot be any larger than the square root of L1, L2. It cannot be any larger than that. That's the restriction. So you can never have an M larger than that. So if I have L1 is 1 and I have L2 is 1, M cannot be 3. Cannot be. Can't be any larger than square root of 1 times 1, square root of 1. It can't be any larger than 1. So there's a restriction on M. And if you think about that, it's because you're self-inducted. You can't get more from the mutual inductance than the self-inductance. So when K equals 0, I would say the following. This is all leakage flux. And when K is equal to 1, there is no leakage flux. That's just for you, for your feel, so you get a sense of what's going on. When it's 1, all of the flux is coupled from one coil to the other, right? It's the coefficient of coupling. It's all coupled. All right, there's also another important relationship that we need before we can move forward. And so another important relationship is the ratio of the turns. The turns do two things for us. The turns will allow more flux to be generated and will allow more flux to cut through the coils. And so the former tells us how big a magnetic field we create. The latter tells us how much of that, of the induced voltage we can get. So one relates to one thing, one relates to the other. So it's the ratio of the turns. So we'll call that, some books use N, I'm going to use A. A is defined to be the turns ratio, and it is N2 over N1. I want you to notice in everything I'm doing today, it's always the secondary over the primary. I2 over I1, V2 over V1, N2 over N1, which is really interesting. What's the smallest the turns ratio can be? The smallest. Smallest it can be is 0. Can't be negative. You can't have a negative turns ratio. N2 could be 1 turn, and N1 could be a bazillion turns. So that it can approach 0. And then the largest it can approach infinity, but it'll never reach infinity because the number of turns is a finite number. So it'll never be infinity. Okay, once we understand those two, now let's go to the ideal transformer. For a transformer to be ideal, the following situations or the following must hold true. So ideal transformers are nice. Number 1, K is equal to 1. It's an ideal transformer. Everything is coupled. All the flux from coil number 1 cuts through coil number 2. So just another way of saying that, there is no leakage flux. Leakage flux. So we have that situation. So that would be equivalent to saying M is equal to the square root of L1, L2. That's the same thing. This one is not easily understandable. The self-inductance of each coil. It approaches infinity. L1 equals, I shouldn't write equals. L1 equals infinity. L2 equals infinity. I don't want to write that they're equal. Both of them are infinity. Number 4, and this is why a lot of people don't put this in up front. The coil losses are negligent, or I'm going to call them 0. There are no losses. What does it mean to have losses? It means we're losing power. Some of our power is lost in the coils. Well, we haven't learned a lot about power in inductors, but inductors, pure inductors and pure capacitors do not dissipate any average power. Only resistors do. So this means R1 equals R2 equals 0. There's no internal resistance in those coils. And then finally, the last one is the ratio L2 to L1, because I said they're not equal. That's why I was careful about that, writing that they're equal, is equal to N2 squared over N1 squared, which is equal to A squared. A couple of different ways we can write that. Or we can write L2 equals A squared, L1, or we can write L1 equals 1 over A squared L2. And you just have to take this for what it's worth. So I just pop my image up there. It's really interesting what's going to go on with these ideal transformers and what falls out of the equations and just melts apart based on this. So what you have to understand is the following. This seems awful bizarre. I'm looking at this and like, L is equal to infinity, Dennis, really? All right, let's get a realistic situation. You just have to trust me on this. In an ideal transformer, these things are true. In a real transformer, they're so darn close, you can't believe how darn close it is to be in an ideal transformer, that those inductance values actually approach infinity. And I want you to think about this when you're concerned that, like, come on, how does that happen? How does a resistor's value approach infinity? I want somebody to answer that question for me. How does a resistor value approach infinity? What do I do?
Drive a lot of current into it.
Okay, we drive a lot of current into it, but we want it to be infinity. So if it's infinity, no current's going to want to go through it. No current wants to go through what? What do we know of that no current goes through?
Open circuit.
There you go, an open circuit. So an open circuit is a model for an infinite resistor. So we just use a non-conductor. So you can have inductors whose values approach infinity. Don't think it doesn't happen. So here's the only difference between the ideal transformer and an actual real transformer. So an ideal transformer is going to assume that it behaves in many ways sort of like a linear circuit, and we're going to neglect all the nonlinearities. In a real transformer, there are nonlinearities, but they truly are negligible. They truly are negligible. So as we go back to our work, what we're going to do is we're going to take that information, and the first thing I want to do now is I want to tell you that we draw an ideal transformer in a very particular way. So here's how we draw it. So this is the schematic model, the schematic representation. In most schematics you find, they're actually going to show this with a lot of coils, and you can understand why, even though it's an inductor. So they show a lot of them. For you and me, it doesn't matter. You want to do this? That's just fine. But in textbooks, you'll find a lot of coils usually. Here's what tells you it is ideal. You ready? Not this. So I'm just going to put those dots there, keeping in mind the dots can go anywhere. I could have done not there. I could have done that. That's an ideal transformer. I could do this. That's an ideal transformer. I could do this. That's an ideal transformer. Well, how do I know it's ideal, Dennis? Here's how you know it's ideal. Are you ready? There are two things you're going to see. That's number one. That tells me it's ideal. The other thing that I'm going to see is one of the following, something that looks like this. N1 equals 1,000. N2 equals 4,000. So they actually give the number of turns. Okay? Notice over here, there's no current, there's no voltage, there's no inductance value, no inductor value, no inductor values. You want to know why? Because an ideal transformer, first of all, we know that it goes to infinity, doesn't need any inductance value in order for us to be able to work it in the circuit. We're going to find some really cool things about it. So that's one way to do it. I'm going to give you another example. And I'm just going to draw these quicker for you. Same thing. You got to have the dot notation somewhere. There's the dot notation. Doesn't matter. But then we can do the following. 1 to 4. And I love this because this is how we talk about ratios of turns, right? Our A is equal to N2 over N1. And all this is saying is the ratio is 4 to 1. The ratio is 4 to 1. It doesn't say N2 is 4, and it doesn't say N1 is 1. It does not say that. Here's another way I could do the same thing. Instead of 1 to 4, some people do it 1/4 to 1, like that. And there's a reason they do this as well. And that's because, remember, this 4-terminal device I can use in any direction, correct? So this transformer here can look like a 4 to 1, but it can also look like a 1/4 to 4. It depends on whether or not I treat this as the primary and this is the secondary, or if I treat this as the secondary and this is the primary. So this and this really are useful depending upon the notation. So up here, it gives us the actual number of turns, and you'll see all of those notations used. So I'm not gonna focus on the notation that's used because we should be able to handle any of them. All right. Usually when we get a transformer, what we do in the circuit, I didn't do it here, is we label an I1 and an I2. And I'm gonna tell you right now that for most I1 and an I2, usually we like this. And the reason we usually like this is because of the signs that we talked about earlier. So then we do the following, plus minus V1, plus minus V2. So the V2 would tell me that's the secondary, it's not the primary. And the V1 over here would tell me it's the primary, it's not the secondary. That's what it would tell me. All right, that's the schematic diagram. Great for the schematic diagram. Now let's get to the good stuff. The good stuff. Let's start with the relationship between I1 and I2. So remember, I2 over I1 was equal to j omega m divided by Z22, and Z22 was R2 plus j omega L2 plus Z sub L. Keep in mind, Z sub L can be complex. It can be complex. So here's what I'm going to do here. I'm going to substitute in the following. I'm going to substitute Z sub L is R sub L plus J omega. I'm not omega. I don't want to put an omega in. J X sub L. Okay, though just one of the ways that we can write an impedance. It just says that it has a resistance and a reactance. Okay, also we're going to substitute in R2 is equal to 0. So let's see what this gives me over here. This gives me j omega m divided by, that's 0, j omega L2 plus R sub L plus j XL, which we know we can write this, we can group the j terms, j omega m divided by RL plus j omega L2 plus XL. So we're just in the complex world of mathematics. All right, now let's see what happens in the ideal transformer case. So in the ideal transformer, well, let's see. In this equation, what's going to be important to us? What's going to be important to us is we know that L2 is going to approach infinity. But we don't want to just throw the infinities in there yet. We don't want to do that. So when we look at that, if L2 approaches infinity, that's that number there. What do you think about X sub L? What do you think about X sub L compared to omega times L2? What do you think about X sub L compared to omega L2? L2 is infinity. It's really big. Tell me about X sub L.
0.
Yeah, it's negligible. It's therefore X sub L is negligible. It's like it's 0. Its value is not 0, but it's so small. It's like having 56,332,000 plus 0.001. What do you think about the 0.001? It's really small, right? It's negligible. So that's out. Okay, now, what about the R2? I'm sorry, the R sub L. What do you think about the R sub L? So I want you to think about this from the complex plane. Here's R sub L. It's on the real axis, like I'm over here. And then JX sub L is, there's not X sub L. This is omega L2, is all the way up here. So follow that all the way up, and we've got that right there. Is that approximately just equal to J omega L2? I've got this. Is that about the same as this right on the axis? What do you think?
Yeah.
Yes, it is. So this is negligible also. I know it's real, but it's small. It's like having J a billion plus 1. Well, 1 is nothing. The magnitude is about a billion. So therefore, what we have now is I2 over I1 is equal to J omega M divided by J omega L2. This is unbelievable. The J's cancel, the omegas cancel, and this is M over L2, which seems like we're stuck. But don't forget, M, for the ideal case, M equals square root of L1, L2 in the ideal case. So let's substitute that in. Square root of L1, L2 divided by L2. I'm going to write L2 the following way. The square root of L2 times L2. And you can see that that cancels, and I'm left with, it is the square root of L1 over L2. Square root of L1 over L2. L2 over L1 is A squared. So now we have it's the square root of 1 over A squared, which equals 1 over A. Wow. Are you kidding me? Here's the result that what we just showed. I2 over I1 is equal to 1 over A. Leave a little space in there, 1 over A. Do you remember how I neglected way back a long time ago? I told you we could get a positive or a negative sign. Do you remember all of that? That's the ratio of the currents in an ideal transformer. Or two other ways to look at it. I2 is equal to plus or minus, excuse me, I2 is equal to plus or minus 1 over A I1 or I1 is equal to plus or minus A times I2. All three of these are the same thing. I don't care what equation you like, use whichever equation you like. They're all the same equation. That is an unbelievable result. All I need to know is the ratio of the turns, and if I know the ratio of the turns, I can figure out from one current what the other one is. So that is a powerful, powerful result. Okay, let's do the same thing for the V1 and the V2. The results that I boxed up for you, those results, that's what I want you to know. Everything else that we did boils down to just getting these equations right there that we just got. That's what I want you to know. So now I'm going to start with equation 4 and equation 2. So V2 over V1. So we had that earlier. J omega M Z sub L divided by R1 Z22 plus J omega L1 Z22 plus omega squared M squared. So we have that. Okay. And so let's group back together. J omega M Z L. I'm just going to take this slowly and carefully with you. I'm just doing math. And just there's my Z22 factor because I'm going to put in Z22. So it multiplies R1 plus J omega L1 plus omega squared M squared. You must be really careful. You can't just immediately put in, oh, M is equal to infinity. You can't do that. You have to look at ratios of things and ratios of numbers. Okay, so that's equal to numerator, J omega M Z sub L, big denominator coming up, R1 plus J omega L1 times Z22, here's Z22, R2 plus J omega L2 plus Z sub L plus omega squared M squared. All right, ideal. Zip, zip, R1 and R2 are equal to 0. So those terms are gone. So now I have J omega L1 times this J omega L2 there. So let's go ahead and multiply that through. So this is equal to J omega M ZL. So this is omega squared M squared. That's this term. And then I get a real when I multiply here and here. Minus omega squared L1, L2. Okay, those are the real terms. And then I also have J omega L1 times ZL. We don't know if that's real or not because ZL in general is complex. So just plus J omega L1 times Z sub L. Anybody help me with this term right here in the ideal case? Whoop. What's omega squared M squared minus omega squared L1, L2?
Is it infinity?
Nope. L1 is infinity, L2 is infinity, M is infinity. But look at what I'm doing. I'm subtracting, so this group, I can factor this out, and then I get M squared minus L1, L2. Ideal case, ideal case, ideal case, ideal case. M right here. So M squared equals L1, L2. M squared is L1, L2. M squared is L1, L2. Now what is this all equal to?
Zero.
Unbelievable. The Z sub L's cancel. It has nothing to do with the impedance. Nothing to do with the impedance. Nothing to do with the frequency. Unbelievable. Transformers, frequency doesn't matter. Doesn't matter what the frequency is to the transformer. Behaves the same way. And so this is equal to M over L1. Let's play that same game. Square root of L1, L2 over square root of L1, L1. And this is equal to 1 over A, or just A. L2 over L1, just A, all of that. So here's our result. You ready for the result? What you're responsible for, what you need to know? The result, it's beautiful. It is V2 over V1 is equal to, again, we have to throw the plus or minus in there, plus or minus A. Another way to write it, V2 is equal to A V1. Another way to write it, V1 is equal to 1 over A V2. And this is the power of transformers in transmission lines. And we don't know yet why, and I'm not sure we'll cover it in this course. But in transmission lines, what you do is you put a transformer in there and you change the voltage. You change V2 to be A times V1. So we take a small voltage, we step it up to a big voltage that drives the current down, it drives our losses down. We transmit the high voltage, and then we get to the point where we want it, we step it back down using an inverse transformer, flip it around the other way, and we step it back down to a voltage that you absorb in your house. That's why power lines are real high voltage, but the voltages in your house are small. Okay, plus and minus in all of these. I apologize for missing that. Plus and minus in all of those. So notice it's kind of the opposite of what the current does. The voltage does the opposite of what the current does. Okay, the last one is on the impedance. It's ZAB. And you can play the same game if you want to with regard to ZAB. So ZAB for an ideal transformer. So ZAB for an ideal transformer. What happens with ZAB? So when you're looking at ZAB, what you get is the following. And you can prove it easily using the I1s and the I2s if you want to. You can use the I1s and the I2s. But I'm just going to skip over it and give you the result. Here's what it is. ZAB is equal to 1 over A squared times C sub L. So what happens is the reflected impedance that comes back, this ZAB, the reflected impedance that comes back pertains to Z sub L, but that's not, this is not the reflected term. This, I want to remind you, this is both the reflected term and the impedance of the primary. And the impedance of the primary. All right, so how might we use something like that? The way that we would use it, believe it or not, is really cool. So you have a transformer, and it's set up like this. I'm going to show you something. I'm going to tie this all together. I'm actually going to put this in here. I'm going to make it an impedance, Z sub S, and my source, plus minus V source. Over here, by the way, did you notice on this one with the 8 plus or minus A squared, It doesn't matter where the dots are. It doesn't matter where the dots are. Okay. So I have, this is all the transformer here. And on the secondary side, I have a load right here. And on the primary side, I have my source over here. So what happens is the following. Let's just, I'm gonna put in a turns ratio. Okay, so let's put in the turns ratio. I'm gonna make up a turns ratio of 1 to 10. That's the turns ratio. So what happens is this is equivalent to the following. Remember, ZAB is here to here. So that's A, that's B. So we can do the following. Now there's A, there's B. And in this example, this is equal to 1 over A squared. Can you tell what A is by looking at this? What's A equal to?
Is it 10 over 1?
Correct. A is 10 divided by 1, which is 10. That is correct. So what happens is when I bring it over to the primary side, watch what I get. I get 1 over 100 times Z sub L. It takes that impedance and it looks different. Now look at this circuit. If I do this with resistors, you would understand that if I did it with resistors, it would look like this. And that looks like a max power problem, correct? So this is why transformers are used to match impedances. Because when I take this impedance here and I want to get it to the other side, I want to get it over there so that I dissipate the maximum amount of power. An ideal transformer dissipates 0 power, so all of that power would be dissipated in the load. I get max power to the load. We just don't know what that max power is for a complex impedance. We don't know yet. Okay, so let's end on that right now. Stop my share. This is still part of the chapter. I did not give you any transformer problems in your chapter. I don't like any of the transformer problems that are back in your chapter, but this is still part of the same chapter with the sinusoidal steady state, which I believe is chapter 9. So it's all still part of the same chapter. What we'll do the next time when we get together is we're going to do a couple of transformer problems so you can see how to use this to solve problems with transformers, how it minimizes, just like an op-amp minimizes your equations because the 2 input nodes to the op-amp have the same voltage. We've got a relationship with these voltages here. So it reduces your equations by 1 when you use a transformer in your circuit. So we'll take a look at some transformer circuits, solve 1 or 2 problems with transformer circuits, and then we're going to move on to looking at, great, we did all this sinusoidal stuff with phasors. We're still using phasors here. What about when I don't have sinusoidal inputs? Then what do I do? And the answer is we use Laplace transforms. So we're going to step into the world of Laplace, more mathematics, mathematics, mathematics. Then we'll tie the math to circuit analysis. Any questions before we part ways today? Hearing none, I'll get all of this saved to you so that you have access to it quickly. And I will see you on Thursday. Have a great day off tomorrow and stay safe. Bad times out there. Stay safe, everyone. Take care.